Welcome to Algebra 1, Semester 2, Unit 10. This is the very first section of Unit 10. It's on geometric sequences and discrete exponential functions. As you can see, we have 1, 2, 3. These will probably be separate videos. 4, 5 videos in this section. Remember, feel free to use these videos in conjunction with Khan Academy or other videos out there. All you need to do is look up the topic that's in the notes and then go practice it on other sites as well. I have one student who's doing all of the practice problems off of Khan Academy that goes along with the topics rather than using the book. And that's just fine. Just make sure to write it down. Write down your notes from the Khan Academy as well as the problems that you do and use those in conjunction with these notes. That's just fine. Okay, discrete exponential functions. We will work on those in class. Remember the difference between discrete and continuous linear functions, and then we'll work on this in a lab with bouncy balls. So make sure and ask me in class for that work. And then let's go on to geometric sequences. We have worked with linear sequences and arithmetic sequences. In geometric sequences, let me just give you an example. And you've seen these in class, but a linear sequence we might have would be 3, 5, 7, 9, and so on. And the geometric could start at 3, but then it would go to maybe 6, 12, 24, and so on. So you ask yourself, well, how can you tell one is the one from the other? Explain to me how you would get from this to that number. And can you do the same thing to get to that number? And the same thing to get to that number. When you come up with that pattern, then you found the rule for this linear or arithmetic. Maybe I should write arithmetic. We convert it to a linear function, but it's really an arithmetic sequence. Just a slight difference there. But anyway, the arithmetic sequence is 3, 5, 7, 9. Now, what's the rule to go from one number to the next? You might say, well, you would be adding 2. Because you're adding or subtracting, that makes it arithmetic. So plus or minus is what's causing that to be the arithmetic. Now, when we come down to this one, the geometric sequence, what rule can we use to go from 3 to 6? And the same rule to go 6 to 12. If you say it's multiplying by 2, then that's how you can see that it's a geometric, is that it's involving a factor. A factor. Okay? So, when we look down at the questions at the bottom of the page, we'll come back and do those formulas in a minute. But if you look at this sequence, we have 4, 8, 16, 32. What are we doing to go from one to the next? Well, that's how we determine whether or not it's a geometric sequence. Does it have a common factor? Is it being multiplied? We call that a common ratio because sometimes it ends up being a fraction and you feel more like you're dividing than multiplying. Remember, dividing by a whole number can be the same thing as multiplying by a fraction. Using this technique, given in problem number 1, the common ratio, can you prove that this is a geometric sequence? Well, you could all see that this was being multiplied by 2. But there is a little tactic and a trick that you can use to make sure that that's your common ratio. What you do is you take the sequence and you take any numbers in it that are right together, and you put the right one over the left. So 8 over 4. Does that equal the ratio that you're thinking, which is 2 over 1? Now the trick is, if it is truly a sequence the whole way along that follows this rule, then every single one of these will equal that 2 over 1. 16 over 8, does that equal 2 over 1? Sure does, because 8 times 2 is 16. And 32 over 16 equals 2 over 1. Because they're all equal to 2 over 1, it is a common ratio. So the next question asks for the explicit and recursive formulas. We have worked on this in class with different lab setups. If you've been there, then we've had a few different lab setups with tiles and bouncy balls and things that way. So these formulas, this is the term number you're looking for. Like if I say find the fifth term, you're going to put a 5 in there for n. This is the first term. Because it has a 1, it means first term. So it's the very first number in the sequence. The n is from the term number that you're looking for. Okay? And the r is your common ratio. Now that's for the explicit rule. Some of you in class came up with the recursive rule the other day. Recursive, you can remember, because it recurs. It's from the recurring pattern from the one before it. So since you don't have anything recurring before the first term, that's a typo. It should just be the first term is given. It has to be given because you can't find it from a previous term. Now, this is, again, the term number that you're looking for. N minus 1 means the term before that term, so the previous term. You're just taking the previous term and you're multiplying it by your common ratio. That's all that the recurring rule is, or the recursive rule. Now if we come back down to the sequence that I'm helping you with, we would give each formula for the sequence, this is a typo, it should be for the fifth term. So in the problem you're going to work here in a minute, that should be for the fifth term as well, down on number 6. Sorry about that. So for the explicit rule, we know the explicit formula is Fn equals F1 times r to the n minus 1. Well, we know that we're looking for the fifth term, so we're going to plug in f of 5, which means the fifth term. F of 1, we look in this pattern that I gave you, the first term. That's what that means. F of 1 is first term is 4. We multiply by r, our common ratio, which was 2, raised to the power of 5 minus 1. 5 minus 1 would be 4. So we have 2 raised to the 4th times 4 equals our f of 5. Well, 2 raised to the 4th is 16 times 4 would be our f of 5. 16 times 4 happens to be 64. Okay, now in the recursive rule, we have f of n equals f of n minus 1 times the ratio, common ratio. Our f of n is f of 5 because it's the fifth term we're looking for. So the f of n minus 1 would be f of 4 times the common ratio, which is 2. Now our fourth term would have to look up here, and we see that it's 32, so we take 32 times 2 equals our f of 5, which is our fifth term. So our fifth term equals 2 times 32 is 64. When you work out the recursive rule and the explicit rule, they should end up being the same if you're looking for the same term in that sequence. I want you to make sure and do this. I will be checking it in class with you to make sure that you've gotten these, so come ask me if you have trouble or ask another lab partner. Over to the next page. Page number 3. We have a few problems here. I give you just a few facts. You have to determine which to use, the explicit formula or the recursive formula. Remember, explicit formula uses the first term and the common ratio, and the recursive formula uses the previous term. Those are the biggest differences in them. They both use the common ratio, but recursive uses previous term, explicit uses the first term. So a geometric sequence has a common ratio of 4. If you know the sixth term, how could you find the seventh term? Well, sixth term is the previous term, isn't it? So I would write down here, I guess I could use the recursive formula. And then I go ahead and write f of 7 equals f of 6 times the common ratio. And I fill in f of 7 equals the f of 6 I gave you was 30, and the common ratio was 4 times 4, so f of 7 is 120. Okay? Geometric sequence has a common ratio of 3 and a first term, which is 1. Well, that means we should use the explicit formula. So f of, we're looking for the 8th term, f of 8 equals f of 1 times r to the n minus 1. Well, 8 minus 1. So we have f of 8 equals 1 is our first term times 3 to the 7th. Now, I would highly recommend that you use a calculator just to double check your work if you decide not to work it out. So 3 to the 7th, just to show you how you use the keys, you would go 3 raised to the 7th and hit enter. And it gives us 2,187. And then you multiply that by 1, it'll still be 2,187. Okay? First term of a geometric sequence is 27. The common ratio is 1/3. Explain how you could find the fourth term of the sequence. Well, f of 4, taking the first term times the common ratio, 4 minus 1. And I would write using explicit formula. Okay, and that just allows me to know this is what I would do. Next one. What information do you need to know in order to find the fifth term of a geometric sequence using explicit rule? You need to know you would need 2? No. We're using explicit rule. Which is it, the first term or the previous term? If you look at the top of the page where I had you write those notes, you would have said you need to know the first term. And what's the thing that you need to know for either formula? Common ratio. So what is the recursive rule for this sequence? Well, the thing that the recursive and the explicit both share is this common ratio. So we know that f of n is going to be equal to f of n minus 1 times that common ratio, which is 4. So there's your recursive rule. Using the given formula, fill in the t-chart, then graph the function on a separate sheet of graph paper. Okay? We'll just fill in our first term, second term, third term, and fourth term there. If we put 1 in there, 1 minus 1 is 0, so 3 to the 0th, any number to the 0th power is equal to 1. 1 times negative 2 is negative 2. 2 minus 1 is 1. 3 to the first is 3 times negative 2 is negative 6. 3 minus 1 is 2. 3 squared is 9 times negative 2 is negative 18. 4 minus 1 is 3. 3 cubed, you memorized the other day, is 27. 27 times negative 2 is negative 54. First term is 10. Second, third, fourth. So the second term, well, we're going off the recursive, and we say that our common ratio is 0.8. So our second term, we plug it in here, f of 2 minus 1. So we take the first term and we multiply by 0.8. That would become 8. And we take the second term and we multiply it by 0.8. This is what recursive means, just taking the previous term. 8 times 0.8 would be 64 with the decimal in between. So it moves over one place due to this one. 64 times 8 is 512. We've got 2 decimal places, so it's 5.12. Are these graphs, are these linear graphs? If we have the exponent in the, or the variable in the exponent, that's an exponential graph. And this one, we're not adding to go from one to the next, so it's not linear. So the answer would be no. Now, if you graph these, you may not recognize the shape yet, but the first one, it should have had a shape that curved down sharply like that. And the second one would have had a shape that curved down like this. Those curves are called exponential functions. And it occurs because each previous term is a factor of the next one. It's multiplied by a factor. That's the end of this section. Thank you very much.